Thank you very much. Yes, good morning, everybody. It's great to be here. So my role at UCL is as a space scientist. I do solar physics research. And perhaps I can use this microphone. Can you still hear me at the back okay? Yes, great. So not that. So my work at UCL is based around looking at our local star, the sun, and understanding why we have activity taking place in the atmosphere of our sun. Now, because the sun is a very physically interesting and very aesthetically interesting object, I started to get into communicating the latest research in solar physics to the public. And when you do that, it's all about, well, what does it mean for the person on the street? And it was that interest really that led me into space weather. So there are many ways that the sun impacts our daily lives, and space weather is this actually quite hidden way, but very important aspect of the operation of our technology, business resilience, and so on. So I want to give you a quick introduction to the sun and why it produces space weather. So space weather is the collective term for changes in the near-Earth space environment, so in our magnetic field and the region around. But space weather starts at the sun. And I think it's always useful just to give you some context images. So I've got my electromagnetic spectrum across the top part of it. Hopefully you've done science at some point. I'm sure you have, probably lots of maths too. So this will be familiar with to you. So we normally look at the sun in visible light. We know it emits visible light, our eyes detect it. And when we look at the sun in visible, we see it looking like this. So basically a blank disk, except for sunspots. And it turns out that sunspots are sources of energy in the sun's atmosphere. And they store energy and they release energy. And so the activity that I'm going to show you in the coming slides is driven by that storage and release of energy. So when scientists see sunspots on the surface of the sun in the context of space weather and the physical workings of our sun, we get very excited. Now, what these sunspots are in reality are regions of very strong magnetic field. So the physics that we're interested in, and that I'm interested in particular, is the physics of magnetic fields. So that's the sun in visible light, but we can go to shorter parts of the spectrum, more energetic parts of the spectrum, and the sun starts to look like this. Now this image is at exactly the same time as the previous one. The only thing I've done is change the wavelength of light that I'm using to look at the sun. And now you'll see it's completely different. So this is an image taken in the ultraviolet part of the spectrum. And where the sunspots were visible in visible light, we've now got glowing arches of million-degree gas suspended above them. And if you think back to maybe GCSE physics or something, where you had your bar magnet and your iron filings, and when you sprinkled the iron filings around the bar magnet, you could see these arches in the iron filings because of the shape of the magnetic field. And that's actually, excuse me, what we have happening in the atmosphere of the sun. Everything is pervaded by magnetic fields. And that's perhaps shown even more clearly when we look at X-ray images of the sun. And now you really see those loops of million-degree glowing gas extremely well. But these are just static images. And what I want to get across to you is the fact that the sun's atmosphere is stormy and changing and violent and fascinating. So now I'm going to show you an image of the sun, and actually these images are taken with a satellite called the Solar Dynamics Observatory. It's a NASA mission. You can look it up, lots of images online, everything is freely available, so you can access this almost in real time. If I zoom in to one particular part of the sun's atmosphere, and I then show you a processed movie, you can start to see the structure. So this is million-degree gas emitting in X-rays and extreme ultraviolet light. Now, we process our images so that we see more detail. And if I run this as a movie, I heard that. That was my reaction to this kind of event. So what you're looking at here is a coronal mass ejection. It's not a phrase that rolls off the tongue, but it does what it says on the tin. It's an ejection of mass from the sun's corona or the sun's atmosphere. And these events are taking place all the time. I've chosen the most spectacular one to show you. It's incredibly beautiful. And it's these kind of events that I study in my work. And I'm interested in understanding how these magnetic fields in the atmosphere of the sun can lift up this million-degree gas and throw it into the solar system. So some of the material here is falling back down onto the surface of the sun, but actually what's not seen in this movie is that lots of the material heads out into the solar system. So So we have this dynamic atmosphere in the sun. It's changing all the time. I think this movie probably runs for several hours, something like that, to give you sort of sense of time scale. But it's these kind of data, I think, that have really changed our perception of us on the Earth and our relationship to our local star. So I put this image up. I show this image all the time in my talks. It's taken from one of the early Apollo missions when the first to orbit the moon. And I really like it because it makes us on Earth look like we are isolated in the cold vacuum of the solar system. And space weather, what we've learned about space weather really turns that on its head. So from the early space age, we went from thinking that the Earth was in the middle of nothing to having a view like this. And this needs a bit of setting up. So what you're looking at here is the combined view of two spacecraft. So if you imagine in your mind the solar system with the sun at the center and the Earth orbiting it, one spacecraft was launched from the Earth and then turned to look back at the Sun-Earth line from one Earth. The other spacecraft was put into a different orbit so that it was able to look back along the Sun-Earth line from the other side. And those two views are combined here. So the sun is that very small dot in the center, the very small orange dot in the center. And then all the space between the sun and the Earth from those two perspectives is shown either side. So the Earth is shown on the right-hand side and the Earth is shown on the left-hand side. So these two spacecraft, the stereo spacecraft, allow us to look at what the sun's doing and what it's sending in our direction. And if I run this as a movie, again, yes, I mean, we are not sitting in a cold vacuum. We are sitting in this dynamic environment. We have energetic particles, charged particles, and magnetic fields all the time flooding out from the sun into the solar system, flowing over Mercury, Venus, Earth, Mars, all of the planets, all of the asteroids, forming a huge bubble around the solar system. So when you look at this, I want you to be thinking about the fact that the Earth is sitting literally in the atmosphere of the sun. The atmosphere has a temperature of a few million degrees. It is hot enough so that that atmosphere can actually expand out into the solar system. Gravity is not able to keep it pulled in. So all the time we have this expanding atmosphere we call the solar wind, and then also we have these coronal mass ejections happening at the same time. So we are living in the atmosphere of the sun, and space weather is driven by changes in the atmosphere of the sun. And these changes originate due to coronal mass ejections, which is something I showed you earlier. This is another processed image now showing the bubble of the eruption heading off into the solar system. So this is literally an ejection of plasma, of electrically charged gas and magnetic field. We have these eruptions ploughing out into the solar system and then acting as a particle accelerator. So actually, to give you some timescales maybe, coronal mass ejections will take maybe 1 to 4 days to travel to the Earth, as will the solar wind. These high energy particles get accelerated as this huge barreling coronal mass ejection heads out into the solar system. Could be with us in under an hour. So very high energy, very fast particles. And then we have another form of solar activity that we call a solar flare, and that again does what it says on the tin. It's a flash of light in the atmosphere of the sun. Light emitted at not only visible wavelengths, but ultraviolet wavelengths, X-rays, and perhaps even gamma rays too. So I think this slide kind of encompasses the 4 types of activity that we're interested in for space weather. One is this constant outflow of the solar wind. 2 are the coronal mass ejections, bubbles of magnetic field and charged gas. 3 are the energetic particles, like a lighthouse beam sent towards the Earth or other places in the solar system. And then solar flares, flashes of high energy radiation. And it's these types of solar activity that Mark and Ewan and will talk about, sorry, Andrew will talk, looking down the panel, Andrew will talk about in terms of the impact and the forecasting. So when we have a coronal mass ejection arrive at the Earth after 1, 2, 3, 4 days, it can, if the conditions are right, drive what we call a geomagnetic storm. Now, the terminology is not so important, but the impact is. when the Earth's magnetic field is disrupted by the impact of this coronal mass ejection, we can see many different impacts on many different types of technology. So electricity network interruptions, if you have loss of power, you can have cascading failures from that, charging on our spacecraft, errors in our global positioning satellite systems. When you have the energetic particles coming in, they can barrel through the Earth's magnetic field and into our atmosphere. So the kind of impacts that we're understanding now in relation to energetic particles is based around ionizing radiation that might be dangerous to the human body if you're an astronaut. Okay, that's a small percentage of the world's population, but maybe if you're flying on aircraft too at a high altitude, and perhaps also to aircraft electronics as well. And then with solar flares, when they send their light towards the Earth, some of it gets absorbed by the Earth's atmosphere. That heats it, causes it to expand. That can have an impact on satellite orbits and also on the level of, or the conditions in our upper atmosphere that are important for radio communications. I wanted to show you this slide here, which is a visualization from the University of Michigan, showing how dynamic the environment is. So I showed you the movie of the solar wind and these emissions coming from the sun towards the Earth. When it reaches us, it means that the Earth and its magnetic field, which is illustrated here by black lines, gets sort of buffeted around as if it was like a windsock. And in a 15-minute talk, I can't go into all of the science, or even much of the science, but it's this dynamic nature and these changes to the Earth's magnetic field that are at the heart of the science behind space weather. Changing magnetic fields leads to electric fields, electric currents. Electric currents are the flow of high energy or charged particles, and it's those currents that are important in the space weather impact. So, have I got a few minutes left? Yeah. So, I wanted to give you a case study of one particular time where we had very stormy space weather, and the time I've chosen, there's many of them, but there was an event at the end of October, start of November in 2003. And I remember this really clearly because I just finished my PhD in solar physics and I was interested in space weather, interested in science communication, and then suddenly this event happened. So this movie shows the sun over several days, and you can see time and time and time again these huge white clouds, which are coronal mass ejections leaving the sun. Then we have the arrival of the charged particles, the high energy charged particles, and we have flashes of light in the atmosphere of the sun, which are solar flares. So the coronal mass ejections are these white bubbles moving away from the sun. The energetic particles show as this snowstorm on the camera because as the high energy particles collide with our detector, they set up a little electric current, and that gets measured. And then we have our solar flares. So in just a series of a few days, we had huge amount of activity, and space weather was starting to get into the mind of the media as well. And so for the first time our department was being called non-stop by the media to find out what was happening. They wanted to know, and that's something that carries on till today. I mean, I've lost count of the number of times the Daily Mail has had a headline that space weather is going to destroy your life on Earth, but it won't, and it didn't at this point in time, and this was pretty severe space weather. But you can just see the number of charged particles hitting our detector at this time. So the impact of these storms that we call the Halloween storms was assessed, and I've kind of split it into different areas. So Ewan will talk much more about satellites, and I will, and the rest of the panel will too, on the other areas. But we did have significant satellite interruption. One scientific satellite was lost altogether. There was an effect on the electricity distribution network in Sweden, where they had a partial blackout for about 1 hour, affecting 50,000 people. I remember the effect on aircraft because we were working with a particular airline at that time looking at space weather, and their fleet were grounded initially while they assessed the situation, but then certainly aircraft were rerouted because of these radio blackouts that happen due to the solar flare changing the upper atmosphere and the radio propagation, and it becomes difficult to fly over the polar regions because of that. there was errors in the GPS positioning, and then also for human health. Astronauts on the International Space Station took shelter, and high latitude flights were reduced in height to bring them into a thicker part of the Earth's atmosphere to give them more shielding from the particles. So I hope that has given you a kind of overview of space weather origins of the solar wind, solar flares, coronal mass ejections, and the particles. Now, when it comes to predicting and assessing the size of the impact, there is a storm scale given that goes from 1 to 5 with increasing severity. I'm not going to talk about that too much because that overlaps on Mark's area, but what I want to say is that a lot of the scientists in the UK are now working with various industries to help understand what space weather means for their organisation. And this is a slide that was put together whilst I was working with a particular finance company. So they took the space weather scales on the left-hand side from 1 to 5, mild space weather to extreme space weather. And we talked through the impact. And that allowed them to look at the probabilities, because we have the data now that allows us to work out what the probability of certain size storms is. And from that, they then looked at, right, well, what's the impact going to be? How likely are we to have interruptions to our power, internal, external? How likely are we to have travel disruptions? We even considered things like reputational damage. So what would it mean for this company if they lost their power and all of the other finance companies continued to work? Communications were in there. And then through this mapping, we came up with an impact score that allowed them to then take their, look at their business resiliency planning and try to mitigate some of the risks. But when it comes to space weather forecasting, there are still significant challenges because we are still developing our scientific knowledge. So one of the messages that as scientists we want to put out is that we need good and reliable data. And we need data that's delivered in a timely manner too. So I want to just very briefly raise with you a new mission that we're developing at the moment. So the situation is that we know space weather is important, we know it has a significant impact. But for the space weather forecasting in this country and in Europe as a whole, not necessarily America, but for Europeans, we are very limited in terms of space weather, operational space weather data. Our data comes from scientific satellites, which are built in a certain way, designed in a certain way, and operated in a certain way for science. So what we want to do now is have a European space weather monitor, and we've called it Lagrange. It's being developed at the moment. We hope it will launch in the early 2020s, but that will enable us to have robust data collected in a timely way from the right point in the solar system as well. And I can talk about that more later. So thank you very much for listening.